We start off Chapter 6 with a set of 3 theorems that are used for calculations, not so much in proofs. As you work on this section, both the video and the problem set, you will want a calculator handy in order to do these calculations. First, a quick note before we get going. All polygons in this section will be convex polygons like these. All of these polygons pass the so-called rubber band test. None of them go in on themselves. We won't have any concave, otherwise known as non-convex polygons in this section. No polygons like any of these here. The formulas in this section only work on convex polygons. It's good that convex polygons are far more common than concave ones. Now a few vocabulary things to get out of the way before we get to the formulas. An equilateral polygon is a polygon with all sides congruent. An equiangular polygon is a polygon with all angles congruent. I've mentioned this before, but when we dealt with triangles, every triangle that is equilateral was also equiangular and vice versa. However, that is only true of triangles. It does not work for any other polygon. The easiest example is with quadrilaterals. This quadrilateral is equilateral. It is known as a rhombus. All of its sides are congruent, but this rhombus is nowhere near close to being equiangular. It has two extremely obtuse and two extremely acute angles. This quadrilateral is equiangular. You might know it as a rectangle. This rectangle is nowhere near being equilateral. It has two very small and two very large sides. Students sometimes get these screwed up, so just make sure that you know that only triangles does equilateral mean that it is also equiangular, or vice versa. It doesn't work for any other polygon. Finally, we have a regular polygon. A regular polygon is a polygon that is both equilateral and equiangular. Here are some examples. You'll notice that all of the shapes have a lot of symmetry in them, and they call these regular. I guess that means that the rest of them are irregular, or mutants, or something. Now we get to the first theorem. It is used to calculate the sum of all the interior angles in a polygon. Rather than just give you the formula though, I'm going to walk you through how the formula came about. First, we have a triangle. We have already established with the triangle AngleSum Theorem that the interior angles of a triangle always add up to 180 degrees. That's step 1. Let's go one step further. Here we have a quadrilateral. This little thing I'm about to show you works on any convex polygon. You take your polygon and pick out one vertex. Here, I will just randomly pick one. From this vertex, you then draw in all of the diagonals that you can. Remember, it is only from this vertex, not all of the vertices of the polygon. In this case, there is only one diagonal that I can draw in. By doing this, I have split this quadrilateral up into two triangles. The angles of those triangles happen to make up the angles of the quadrilateral. We know that the top triangle's angles add up to 180 degrees, and we know that the bottom triangle's angles add up to 180 degrees too. So our quadrilateral is just two triangles. Each triangle has 180 degrees. So our quadrilateral must have 360 degrees in total. Moving on up, we have a pentagon here. This process works just like the quadrilateral. First you choose one of the vertices. Then you draw all of the diagonals that you can from that one vertex. This splits up the polygon into triangles. Here the pentagon has been split up into 3 triangles. Each triangle's angles add up to 180 degrees. 3 times 180 degrees is 540 degrees, so we can say that the interior angles of a pentagon must add up to 540 degrees. One last quick example on this hexagon. We choose one random vertex, draw every diagonal in from there. In this case, that makes 4 triangles. Each one has 180 degrees, so we can figure out that the interior angles of a hexagon add up to 720 degrees. We could keep going, but there is a pattern here. First, we had a triangle. It had 3 sides, and it had 180 degrees total. Then we had a quadrilateral which has 4 sides. We chopped that sucker up into 2 triangles, each one with 180 degrees. So in total there were 360 degrees. I then moved on to a pentagon which has 5 sides. That got sliced and diced into 3 triangles, each with 180 degrees. So the pentagon had 540 degrees in total. Finally, I showed you what happened to the hexagon. It started with 6 sides, which ended up forming 4 triangles. Each triangle was 180 degrees, so 4 times 180 degrees is 720 degrees in total. Which brings us to the pattern. Use your inductive reasoning skills. What comes next? Look at how the number of triangles compares to the number of sides. The number of triangles was always 2 less than the number of sides. So if we had n sides, the number of triangles must be n minus 2. To find the total degrees, we multiply the number of triangles we had by 180 degrees. So if we have n minus 2 triangles, then we have n minus 2 times 180 degrees in total. That's the formula we need. This is the Polygon AngleSum Theorem we just derived. The sum of the measures of the interior angles of a convex n-gon is n minus 2 times 180 degrees. Simply plug in the number of sides for n, and then let the calculator do the work for you to find the total number of degrees inside the polygon that you have. It's a pretty simple formula. The Polygon AngleSum Theorem works on any type of convex polygon. It doesn't matter how many sides you have, and it doesn't have to be regular. However, if the polygon is regular, we can figure out what the measure of each internal angle is. Regular polygons are equiangular, so each angle has the same measure. For a triangle we have 3 angles, so we just divide 180 degrees by 3. With a square we have 360 degrees total, and 4 angles, so we just divide the 360 degrees into 4 equal parts. With a pentagon we had 540 degrees total and 5 angles, so we divide the 540 degrees into 5 equal parts. I could keep going, but the pattern should be obvious. You first figure out how many degrees total you have, then you divide that number by the number of angles that you have. So we can make a formula out of it. This is the corollary to the Polygon AngleSum Theorem. You do exactly what I just did. You first figure out the total number of degrees in your polygon. That's the top part of the fraction. Then you divide by the number of angles that you have. Remember, this only works, and frankly, it only makes sense, for regular polygons. You can't do this if the polygon isn't regular. Our final formula now deals with the exterior angles. Something interesting happens with the exterior angles of a convex polygon. Let's look at an example. Here I have a triangle. It isn't a special triangle in any way. I just picked one with random measures for angles. If you want to follow along and make your own triangle with your own angle measures, go ahead. Just make sure your angles add up to 180 degrees. Then you can verify for yourself that this works for any triangle, not just the one I presented you with here. Now I said we are dealing with the exterior angles, so let's draw those in. What do the measures of these exterior angles add up to? With some quick calculator work, you should be able to verify that the exterior angles add up to 360 degrees. If you drew your own triangle to see if it worked for your numbers, your exterior angles should also add up to 360 degrees. Here's a quadrilateral with some random angle measures. Once again, you can try your own numbers if you like to verify if this works with any quadrilateral. I need the exterior angle measures, so let's fill those in now. Break out your calculator, and you should be able to quickly figure out the sum of the exterior angles. You can do this for your quadrilateral too if you tried your own. You should find that the exterior angles add up to 360 degrees here too. That's odd. That's the same as the triangle. Let's try one more. Here's a pentagon with the interior and exterior angles already drawn in. A quick check on the calculator, and you find that the exterior angles here also add up to 360 degrees. Twice might be a coincidence, but now we have a trend. The Polygon exterior angle-sum theorem says that the sum of the measures of the exterior angles of a convex polygon is 360 degrees. Always 360 degrees. First time I saw that, I was pretty taken aback. That seemed weird, and interesting, and mathematically beautiful in a way. Yes, I am a math nerd.